we're going to hold it with one hand and hit this with the other, right?
Oh, okay. And
And everyone should be able to see the flash.
yeah, when
like this. You hold it like this, and you touch it on the nail.
oh, okay.
It'll flash.
Oh, so it goes all the way through you. Okay.
Right. But just
the,
maybe people should come close so they can see it.
Actually, it might even. Huh.
I
Might
didn't
work
bring
better
anything to recharge it.
if you just touched it against. It doesn't have to go through you at all. If you touch it
on
the nail, and then let me see. I can extend. You get
I see.
you get more current with less resistance. Right? So.
Well, maybe it'll reach just like this. But then you have to hold it so that you're not obscuring the light. No.
You think it'll touch?
I don't think it'll work.
Try to wrap it around one end of that.
We don't know.
Like that, right?
Yeah.
And then hold this against the side and lean this in.
Yeah, that's what I'm figuring.
Lean that in.
Yeah. See if we do that.
Be skillful.
Okay.
Got one shot.
Yeah, I got one shot.
Okay, well, we have to wait for Drew.
The water's yellow? Are we sure it's water? Somebody's been fooling around with a Leyden jar, huh? Okay. Well, last time we learned about Leyden jars, and this was charged up a couple of days ago, right? So we see if this thing still sparks. Now, what I'm going to do is touch one end of this paper clip to the outside of the jar, to the foil, and then try to touch the other end to this piece of wire that is hanging off, and we've got this little lamp here. Wait, I need to adjust my angle here. Okay. And we should see the little lamp light up. Let's see if it works.
It did.
Yeah,
It did.
It wasn't very dramatic, was it?
It's only a little
Did it
spark.
flash?
It did flash.
Oh, yeah,
It flashed. It flashed.
because when you take it off, then it gets darker.
Okay.
Yeah,
Yeah, we should have dimmed the lights, I guess. That would have worked better. But I was expecting something a little more dramatic than that. But
you don't have to close your eyes or anything. But it did flash, right?
yeah. Okay, so it works. And as we covered last time, it is possible to make Leyden jars better than this. If you coat the outside and the inside in metal, and you say use a little thin glass rather than this thicker plastic, it will work even better. And this in the original, I don't think I gave you a year for when the Leyden jar was invented last time. I think I forgot to do that. But it was 1745 that von Kleist first invented the Leyden jar as a way of storing electricity. And within a year or two after that, people had learned how to optimize the design and store large amounts of electricity. Now, before I get into the main topic today, which I want to cover Benjamin Franklin's discoveries in electricity. There's one experiment that people thought of once they had this Leyden jar that is interesting. I want to tell you about. Selah. Oh, well, we're going to get to Franklin's experiments in a minute. This is an. I'm going to start off telling you. I just want to tell you this one little experiment that somebody thought of doing. It's not Franklin. I don't even actually remember who first did this. But once people had a large amount of electricity that they could store and carry around, they thought of trying to figure out how fast electricity actually moved through a wire. Now remember, does this remind you of anything? Neve?
Can't remember who, but he's trying to calculate the speed of light.
Right. It was Galileo who tried to figure out how fast light moved by doing a lantern experiment where he would stand on one hill and his buddy would stand on a hill a mile away, and they would cover and uncover the lanterns and try to time it. Well, they did the same sort of thing with electricity. Now, you remember that one didn't work out too well. The light one, and it wasn't until much later that scientists, after Galileo, that scientists were able to figure out how fast light moved. And does anybody actually remember? Nick?
They calculated the distance, like whenever the eclipse of Jupiter.
Right. What they needed was a really long distance. Longer than the distance between Galileo's hills. So they ended up watching Jupiter's moons and figuring out that the times of the eclipses of Jupiter's moons depended on where the Earth was relative to Jupiter. Okay, so the baseline they were using in that case, the light was traveling all the way from Jupiter to Earth. And that was a long enough distance, so it took the light a measurable amount of time to travel that. Well, here, somebody set up a wire 2 miles long. All you have to do is basically you take your Leyden jar, say, and you have a wire. Okay, you string it a mile away from you, and then walk back a mile. Okay, you got a length of 2 miles of wire, and and in that case, he didn't have a light bulb, obviously, but he could test with a spark, say, how long it took the electricity to traverse that 2 mile distance. Now, what do you think the result was, Troy?
He couldn't measure it?
Couldn't measure it. Yeah, it was the same as Galileo's light experiment, basically. It was too fast. So all they could conclude was, it's too short a time for us to measure. Ben?
Who was he?
Oh, actually, I don't even know. I don't think this book of mine actually says. They just mentioned that some people had tried to, by 1748, people had tried to measure the speed of electricity up to distances over 2 miles, and no one had been able to time it. But yeah, I'm not sure who did that experiment. Okay, let's start on Benjamin Franklin. Now, Franklin was, you may have heard of, I'm sure you've heard of Benjamin Franklin. You may know something about him from your history classes. He's not primarily known as a scientist by most people, I don't think. He's probably more famous for his politics. Right, yeah. That's Everybody would like that, to see their picture on a $100 bill. So he ended up late in his life being ambassador to France after the American Revolution and the United States became a country. He was our ambassador to France. Franklin was actually very well respected in France. And one of the reasons that he was so well respected in France was because they respected his scientific work that he had done decades earlier. So, in fact, he might have been better known in France for his science than he was in America. But, I mean, Franklin was he did not have an education in science, but he became fascinated with the electrical experiments that were so popular in the 1730s and 40s. And he saw some of these experiments demonstrated and immediately went out and bought the materials himself so that he could repeat the experiments. I mean, the experiments I've been describing to you for the last couple of weeks. But Franklin's first contribution to electricity was not doing new experiments and discovering new facts about electricity. The first thing that Franklin did that was very useful was he came up with a theory, a physical theory of what was going on to explain all these electrical experiments. See, so far, I've taught you, I mean, I've told you about a whole bunch of different experiments and the behavior of electricity that we've seen in lots of different cases. Now, we've seen effects, I mean, you have the Leyden jar, you have electrification by influence, right? Do you remember that one where you could hang, say, an iron bar up on insulated supports and just bring an object that is electrified up close to it, and this end of the bar over here, the far end of the bar, would get electrified, would actually move an electroscope. You remember that one? Okay, we didn't even touch. And then there's the various experiments where people did touch. I mean, they rubbed glass, and you would see the influence of the attraction of the gold leaf, the touch, and then repelling it. Same thing with amber. You saw the exact same effect, but then you saw that when the glass attracted the gold leaf, the amber would repel it, and vice versa. So we've seen all this whole array of facts about electricity, but nobody has tried to explain it yet with a theory. And now, what does the theory give you? What's the point of coming up with a theory that would explain all of these facts? Troy, you have an idea?
Then you could use the facts better, and you could use the force better if you know how it works.
Yeah, I mean, take the discussion that we had last time with the Leyden jar, and you were asking me a whole bunch of questions about, well, how would it work if you did this, or you redesigned it like this? Would it work would it work in that case? And I could answer all those questions, and it's not because I've spent my life playing around with Leyden jars. It's because I know how it works. I mean, I know the theory. And so you give me any new situation, I can figure out what's going to happen. But at this point, see, nobody had a theory. So every fact was just added to this list of facts about electricity that people had to memorize. And they had no way, given a new situation, of figuring out what would happen, because they didn't physically know what was happening in the other situations. Okay, so Franklin realizes that's not a good situation to be in. We need to understand physically what's really going on here. So So Franklin reviews all these, he does all these experiments himself. He repeats the experiments of Gray and Dufay and plays around with Leyden jars and so on. And he comes up with a theory. And his idea is that in addition to ordinary matter, there is an electrical fluid that bodies have and that can be transferred from one body to another and can flow through conducting materials. Okay, so Franklin's theory an electrical fluid exists within bodies. Now, what happens when, according to Franklin, I mean, let's start with the earliest known facts about electricity. You take a piece of glass or a piece of amber and you rub it with wool. Or, now, what is happening, according to Franklin, in that case? Oh, Troy, you already know this?
Well, just guessing.
Yeah, okay.
By rubbing it, you activate the electrical fluid, and then it creates electricity.
Now, according to Franklin, the fluid is always active. Okay, Evan?
The fluid from your hand or the thing you're rubbing it with goes onto the amber,
Yeah, or vice versa.
or vice versa.
I mean, what Franklin said is the rubbing actually causes a transfer of the electrical fluid from one of the bodies to the other. Okay, and when we say a body is electrified, that means it doesn't have its normal amount of electrical fluid. It has an excess amount or it has a deficiency. Okay, so, and either one causes electrification. Okay, so, so let's say non-electrified bodies have a normal or equilibrium amount of fluid. Troy.
So did you think if like one body had more than usual and one had less than usual, they attract?
Yeah, that's exactly right. I mean, we know from Dufay's experiments that there are two kinds of electricity, right? Well, Franklin's got that covered in his theory because what he's saying is that the way you electrify a body, there are two ways you can electrify a body. You can give it an excess amount of the electrical fluid, or you can take some of its electrical fluid away, and it has a deficiency of the electrical fluid. Either way, it becomes electrified. The only way it's not electrified is if it has this equilibrium amount. Nick?
So if you rubbed wool on a glass pipe, would the wool be also electrified?
Right.
Did he?
Right. That's according to Franklin. That's exactly right. When you take a piece of wool and you rub it against glass, say, that, well, what Franklin guesses that glass is positive. Okay, so that glass has, when you electrify it, gets an excess of the electrical fluid. Okay, so what Franklin would say in the case of electrifying a tube of glass with wool is that the glass, that some of the electrical fluid in the wool has been transferred to the glass now, leaving the glass with an excess amount of fluid and the wool with a deficiency of fluid. Yes?
Is there any way you can find out what the equilibrium is?
Oh, no. He didn't have a way of measuring the amount of electricity that something has. Later, people would be able to do that, but yeah.
Is it possible for something to run out of the fluid if you keep using it to rub on something else?
Oh, could you completely deplete something of the electrical fluid? I don't think, because Franklin doesn't have a way of actually measuring the amount of electrical fluid in an object, he can't really answer that question. Troy.
So how would his theory explain like you have the foil experiment that it repels?
Oh, okay. Here's let's take the example of the experiment that we did in last class. Let's say we rub a glass tube, okay, getting it electrified. Now, according to Franklin, the glass tube now has an excess of the electrical fluid. So when you bring it close to the aluminum foil strip that we used last time, say, all right, it will attract that strip, right? Then they touch. Now, what happens when they touch? Troy.
Some of the electrical fluid in the glass would go into the foil?
Right, exactly. So now you've got two objects that both have an excess of the electrical fluid. So if they both have an excess of the fluid, then they repel each other on this. In fact, that's key to Franklin's theory, is that the electrical fluid is self-repulsive. So electrical fluid repels other electrical fluid. Okay, so that explains why two things with glass-like electricity, in other words, with an excess of electrical fluid, is the way Franklin would put it, both repel each other. Okay, because the electrical fluid repels other electrical fluid. Now that brings up a question, though. What if you consider, with Franklin's assumption that that glass has the excess electrical fluid, what does that make amber?
Have the negative or less?
Yeah, that's
amount where it's charged?
yeah, that's exactly. As soon as Franklin makes the choice of saying that treating glass as having a excess amount of fluid, of course, then amber has to have deficiency in electrical fluid, because we know it's the opposite of glass. But why? Now, if we charge up two pieces of amber, will they? How will they interact with each other? Neve, how?
Repel slightly.
Yeah, they'll repel, right? Because now, how is Franklin going to explain that? Troy, you have an idea?
Well, when they get
It's kind of tricky.
when they get charged. Well, wait, are you talking about if they're charged or not charged?
Yeah, they're charged. So we have two pieces of amber that, in Franklin's view, have deficiency of electrical fluid. As I said, both of them are missing electrical fluid. Now we know from experiment that they repel each other. So they're both. Now, the only way Franklin can explain this is on his theory, ordinary matter, absent electrical fluid. Remember, there's two things going on here their body contains. It contains this ordinary matter, and in addition, it contains this electrical fluid. Well, Franklin says ordinary matter repels other ordinary matter. Okay? And the electrical fluid repels other electrical fluid. Now, what holds the ordinary matter and the electrical fluid together is they attract each other. Okay? So it's kind of a complicated theory. But once you have that much, you can explain all of the results of all the electrical experiments that we've seen so far. Yeah.
If that's true, why doesn't everything have repel each other?
Oh, because ordinarily in most bodies, there's just the right amount of matter balanced with the normal or equilibrium amount of electrical fluid. Now, so if you take two bodies, okay, each of these markers has an amount of ordinary matter and the normal equilibrium amount of electrical fluid. So the electrical fluid in this marker is repelling the electrical fluid in this marker. And the ordinary matter in this marker is repelling the ordinary matter in this marker. But the electrical fluid in this marker is attracting the ordinary matter in this marker, and the ordinary and the electrical fluid in this other marker is attracting the ordinary matter in this one. So you've got a balance of attractive and repulsive forces that cancel each other out in the case of two normal objects. Neat.
How come when there's two excess amounts of electrical fluid, it doesn't come together? It's the electrical.
Oh, well, because if both of these have excess electrical fluid, then the electrical fluid repels other electrical fluid, right? So they've got to repel. If they both have a deficiency of electrical fluid, then they'll also repel, but for a different reason, because their ordinary matter then is dominating, and that makes them repel. Oh. Troy.
Does his theory ever say anything about magnetism, or?
No, this is just electricity. Yeah, Franklin never tried to come up with a theory of magnetism. So now let me, now I've just been talking and not writing on the board, so let me try to get some of these points down on the board so you don't forget them. Okay, so let's say bodies with excess electrical fluid are said to be positively charged. I haven't introduced that. Well, I've slipped and said positive and negative a couple of times, but this is the first time I've said it when I was supposed to say it. So Franklin actually introduces these terms of positive electricity and negative electricity, and you can see the way they come out of his theory. Excess electrical fluid is called positive, and deficiency is called negative. That's natural. Neve.
Just thought of something. What about the gravitational theory that says all objects attract each other?
Oh, that's a great question. Neve asks, what about gravitation? Newton's gravitation showed that matter attracts other matter. And here Franklin is saying that matter repels. Well, Franklin would not certainly deny that Newton was right about gravity. But Franklin is saying that in addition to that, the very weak gravitational force that acts between huge objects over long distances, that acts just in the way Newton said, there is, in addition to that, a smaller, shorter range force between bodies that is actually, where matter is actually repulsive. Now, you can't rule that out. So Franklin isn't contradicting Newton's theory. But I think you aren't the only person that thought to ask that question and thought that there was something odd about ordinary matter being repelling ordinary matter. So there were other scientists who thought that was a sort of implausible element in Franklin's theory, and eventually this theory, aspects of it are going to be shown to be wrong, but there's much that's right about it, which is why I want you to know it and see how it explains all the things that we've seen so far. Troy.
Does Franklin do anything to try to prove this theory?
Well, what he does is he points out that there's this whole array of electrical experiments that he can explain with this one relatively simple theory. So that's his evidence for the theory. Now, Franklin never claimed that his theory was proven. He thought it was plausible, a reasonable way to understand this vast array of observations that have been made about electricity so far. And we'll see that when people do discover things that are wrong with this theory, the theory will be easily replaced by something that's a little better in those respects, but some key features of Franklin's theory will definitely be retained. They're true. So this is a good example of how science progresses. You can't expect the first theory to be right in every detail. A lot of times that's not true. But if the theory really did explain a lot of observations, then there's going to be something right about it. And what's right about it will survive, and then people will fix up the parts that were wrong. Okay, so let's continue summarizing some of the key elements of Franklin's theory. So the next one is obviously bodies with deficiency of E fluid are negatively charged. Oh, by the way, I don't think I ever told you, the first guy to start using the word charge talking about electric charge was Dufay. And it just comes from loading they talked about when you load cannons or guns, you were said to be charging the cannon or the gun. And so that's the way Dufay thought of, when you rub the glass tube, you're basically loading it with electricity. So he called it charging. So that's where the term electric charge comes from. Okay, now, so you've got all these points down in your notes, I assume. And let's continue. So basically, Franklin is just well, let me put it another way. That's electrical fluid repels other electrical fluid ordinary matter repels other ordinary matter electrical fluid and ordinary matter attract. And of course, this is going to, as we've already talked about, from this setup, Franklin can explain why any two objects that have the same charge repel and any two objects that have opposite charges attract, right? Now, how would Franklin explain the electrification by influence? Let's go back to this case that Gray, I believe, was the first one to notice. You've taken, say, your iron bar, and you charge up a glass tube, and you bring it up here. Okay, so glass is positively charged, so I'm going to draw those little pluses on the glass. Now, what Gray found was that if he had an electroscope over here, some, say, needle on a pivot, that when he held the glass up to this end of the bar, the electroscope would swing to that end of the bar, showing that this end of the bar has to be electrified now. Now, why would that be? Neat.
The excess fluid goes into the iron bar from the ground.
Well, you haven't touched them now, so there's no, let's say there's no way for the electricity to have gotten off the glass and into the iron. Selah?
Electricity travels.
Well, but where is it traveling? I mean, it's not.
It's traveling through the air and through the iron.
No, it's not doing that. Okay, I mean, if it did that, you would see a spark. Okay, the glass, I mean, sometimes if you get the glass close enough, you could make that happen. You would see a little spark. But let's say he doesn't get the glass close enough to the iron so the electricity actually sparks over. Ben, you have an idea? Think in terms of this theory now. You've got an excess of the electrical fluid here. What is that going to do?
It's going to
Electrical fluid repels other electrical fluid.
Yeah. But the iron bar doesn't have any electrical fluid, does it?
Yeah, it does. It has, what, the normal amount of electrical fluid, right?
Oh,
Because
right.
it's not charged.
Yeah.
Okay, now saying that it's not electrified doesn't mean it doesn't have electrical fluid. It means it has the right amount of electrical fluid, right?
Yeah.
So you have, Nick?
Would it like repel the electrical fluid on one side, push it over to the other side?
Exactly, exactly. That is what Nick suggested, and it's just right. It's exactly what Franklin says. That what's happening here is that the excess electrical fluid on the glass is pushing the electrical fluid in the iron bar. I mean, since it repels other electrical fluid, what's going to happen? Well, it's going to make the electrical fluid pile up on that end of the bar. Over here, it's going to push it to the other end of the bar, right? What?
I was just really surprised that I actually got that.
Yeah, well, it makes sense, though. I mean, it's a good thing to think of, but after you hear it, it makes sense. Oh, so this is Franklin's explanation for this strange phenomenon of electrification by influence. Rachel, are you getting this?
Yeah.
Okay. Neat.
Then wouldn't one side of the iron bar have a negative charge and one side have a positive?
Yep. Yep.
Is that actually true? They
Yes.
try that?
Yeah, yeah. In fact, all you have to do to try that is to, let's say, rather than an iron bar, you have a very light iron needle here that's free to pivot. Well, what you'll find is that if you move this glass tube around, what's going to happen? This iron needle will follow it. I mean, so it's actually attracting with this end, which means this end has to be electrified too. So what you've done now, notice that the iron here in this electrification, but you haven't touched it with anything electrical and you haven't transferred electricity to it. All you've done is you've taken a piece of iron that had the right equilibrium amount of electricity and you've shoved some of that electricity over to one end, leaving the other end deficient in electricity. Okay, so you've made both ends of this iron, you've electrified both ends, but in opposite ways. One end has an excess of electricity, one end has a deficiency of electricity. The iron as a whole still has the exact same amount of electricity it started with, right? It's just now some of the fluid has gone over to one end. Okay, now let's take, just make sure you get this. Let's take a piece of amber instead. And now JJ is going to tell me what happens.
It's a negative charge on where the positive was last time. It's a positive where it was negative.
Yeah, so it's going to, now the amber has a deficiency of the electrical fluid, right? So it's going to actually attract the electrical fluid in the bar toward it, and then this side of the bar is going to be left with a deficiency of fluid.
So will the electroscope repel?
Well, no, the electroscope will still swing toward it, because remember that any electrified body will attract any non-electrified body. Now why is that? No matter whether the electrified body can have an excess of electricity or it can have a deficiency of electricity.
Because it's different from the equilibrium of the electroscope?
Yeah, I mean, what it does is, I mean, if you have an electroscope here, okay, what will happen in this case is that this deficiency of electricity here, the ordinary matter will attract the electrical fluid in the electroscope. And see, what's happening with the electroscope is that it's electrification by influence. So you always attract the opposite kind of electricity to that end of the electroscope.
So does
Nick.
that mean that if something's attracting an object, it's charging it?
Well, if it touches or sparks, but it's charging it in the sense that it's causing an electrical imbalance in that other object. So it's charging one half of it at the expense of the other half, and I ran over my time.
Just like you're taking time at the expense.
Yeah, exactly.